Good morning, all, and welcome to the live stream of LeetCode Weekly 491. Let me just check if the stream is working fine. Good morning, all, and welcome. Okay, I can see the stream is working fine. Just give me a moment to set up the chat. Okay, so now we will dive into the problems of the LeetCode 491. So let's get started with the problem A, which is trim trailing vowels. So the problem itself is very simple. You are given a string S that contains of lowercase English letters, and you have to return the string by removing all the trailing vowels from S. And the vowel consists of A, E, I, O, U. So what does that mean? Means you have been given a string S. It will be any random string A, B, C, D, E, I, etc. Now you have to remove all the trailing vowels. Vowels means A, E, I, O, U. So just erase all of those vowels and return the remaining string. That is your problem. So you can just simply implement what is asked in the problem, right? So what I have done is I have created a isVowel function which would take a character and return a boolean value whether the character is a vowel or not. I'm using a simple OR expression, combined OR expression to get that. And what I'm doing is I am checking two conditions. The first condition is the string should not be empty, should not be empty. If the string is empty and I try to remove any character, then that would result into a runtime error. So sure to handle that case. And second is just check if the last character is a vowel. Last character is vowel. If both of these conditions satisfy, then we can just erase the last character. Similarly here, when I go over here, I can see the string is not empty, but the character is not a vowel. So I will stop and I will return the string. So this is exactly what we are doing. We are checking for these two conditions. If the string is not empty and if the last character is a vowel. If it is, then I will pop back that character and ultimately I will return my original string. So this is the solution for the first problem. Fairly simple. Okay, I can see in the chat that someone has solved two problems, someone has solved three. Okay, great guys. Uh, we will discuss on problem 3 and 4 in deep. First and second were quite simple. There are two approaches for the second problem as well, which I would like to discuss. So yeah, let's move ahead. Thanks for joining guys early in the morning. Okay, so let's move to the second problem. Minimum cost to split into ones. So what is this particular problem? So we will be given a particular integer n and you have to split it into two positive integers a and b such that a plus b equals to x. The cost of this operation is a times b and we have to return an integer denoting the minimum total cost required to split the integer n into n ones. Okay, so let's do a dry run. So let's say we have been given an integer equal to 4. What we can do is we can divide it into two parts, a and b. So there are multiple ways to divide it into two parts, right? I can divide it as 1 comma 3, 2 comma 2, or 3 comma 1. These are the ways in which I can divide it. The cost, if I divide it this way, the cost would be 3 into 1. If I divide it this way, the cost would be 2 into 2. Here the cost would be 1 into 3. This 3, 4, and again 3. So what we have to do is we have to keep on dividing this 4 until we reach 4 ones. You can see, right, if I go like from 4 comma 4 to like 4 to 2 comma 2, then I can go for each 2, I can go to 1 comma 1. So ultimately there will be 4 ones. So I have to go to this state. If my n is equal to 5, then I have to go to 5 ones. So that is the problem. We have to convert the given n into n ones, and what is the minimum total cost required to do that. So the constraints on this problem are really low. You can see that n is less than equal to 500. So n cube solution will work. N cube solution would work. But means like we can also aim for a n square n or O of 1. Anything less than equal to n cube works. So what we can do is we can make a simple observation. For a given n, there are exactly n minus 1 ways in which we can split it. For given n, we have n minus 1 ways to split that n, right? As you can see, to split 4, we had 3 possible ways. To split 5, we will have 1 comma 4 to 4 comma 1. If we go a comma b, like a starts from 1 and a ends till n minus 1. We have total n minus 1 ways to split the given value n. Also, like this is the first thing that we can see in this problem. Second thing which we can see in this problem is there is a overlapping subproblem. For example, here I have 1 comma 3 and here I have 3 comma 1. So if I find the minimum cost for 3 ones, then I can use that minimum cost everywhere, right? Like if I used it while calculating for 1 comma 3, then at the time of 3 comma 1, I can again use that cost. Let's say if my number was too big, it was something like n equal to 6. Then initially I will break into 3, 3. Let's say I go into 2, 1, I go into 2, 1. So if I calculate this value once, then when I come to this particular 3, I won't have to dive deeper into its subtree to calculate its value, right? When we are branching off, we don't need to uh, dive deeper. We can just store the value on its first computation and use it again and again. So that means there is a repeating or overlapping subproblem in this particular problem. Overlapping subproblem. What else can we see? So whenever you see that there is a repeating or overlapping subproblem, it mostly means this is a dynamic programming problem. And the constraints are also really low. Excuse me. Yeah. So the constraints are also really low. Like for each n, we can find in n minus 1 steps the total number of ways to split it. So we can try for 1, then we can go for 2, 3, 4. For each we have n minus 1 ways. So it would be 0, n minus 1 would be 1, plus n minus 1 would be 2, n minus 1 would be 3. And what does this expression evaluates to? Is n into 1, 2, 4 plus 3. So it is in terms of n square, right? Total number of operations computation. So it comes well within our time limits, and there is also overlapping subproblem. So we can try going in the direction of dynamic programming. So let's say how we can model this problem for dynamic programming. So minimum cost for a number. Minimum cost for a number. Let's say I divide that number into two parts, a comma b. Then it would be minimum cost for A plus minimum cost for B. That I will have to find out because that would get added up into the final answer. And the cost to split it into A and B was A dot B as mentioned in the problem. You can see over here. If we divide it into two numbers A and B, the cost is A times B. So this would be our cost. Now what are the possible values of A comma B? A can go from 1 to num minus 1, right? So minimum of this expression for A equal to 1 to A equal to num minus 1. So if we calculate this expression for all possible values of A comma B, then surely like this would be a complete search, right? We'll have exhausted all our options. We will be exploring all the possible options. Then surely from all the possible options we can just take the minimum, right? So this is indirectly you can say a kind of brute force, complete search, brute force kind of thing. We will have to optimize this as well. So what was the optimization which we can add? We can add DP over here. So if the minimum cost for A is already calculated, then we won't calculate it again. We will take it from the results like cash. So we have already like framed it in the form of a sub problem. So the recursion would be really same. It would be something like, let's say this is my recursive function. It would take an integer n, and for that integer it will iterate for I equal to 1 till I less than n, I plus plus, and we will have a global answer initialized with infinity because we want to find the minimum value, right? Find the minimum value, we first initialize our answer with infinity. To find the maximum value, we initialize it with minus infinity. So now we will take answer equals to this whole expression over here. I will just drag it using the arrow expression. That would be just like recurrence of A plus recurrence of B plus A dot B and its minimum with the current answer. So this would be our recursive relation, and ultimately we would return our answer. So that's our solution for the second problem. Now to add the time complexity would be huge. It would be in something like 2 to the power n because there is no cache check added. So we can just insert a vector of int dp and cache these values, and these values will help us solve like reduce the time complexity. So yeah, I haven't implemented it using this method, but this is the first method which should come to your mind when you are trying to solve this kind of problem. So I hope you get this solution. I will now showcase one more method which is based on combinatorics for the same problem. So this is method 2. You can do with any of these methods, but it's always better to know various than this simple return n into n minus 1 upon 2. Yeah, exactly. This is a simple n times n minus 1 upon 2. But what's the reason behind that? How did you come up with that particular formula? Before it wasn't just like saw the problem and that formula came to your mind, right? There might have been some reason or some mathematical explanation for that. So let's dive into the mathematical explanation. So you can see that the original number n. Like I can see in the chat that many of you have tested the formula already. So maybe I will just give some hints for the other folks. So since this was an easy problem, they can also get to the formula by themselves, but I will give a hint. So there would be total n number of ones at the end. Let's say if my n was equal to 5, then ultimately I will have 5 ones. So initially all 5 ones were together in this particular number in this form 1 plus 1 plus 1, and at some point some of these numbers might have separated from the other numbers. These 3 might have separated from these 2 at some point, and that is what we have to calculate, right? If this separated into A equal to 3 and B equal to 2, at some point these 3 have separated with these 2, then again at another point this one will separate from this remaining 2. So it will go like 1 plus 2 and so on. So ultimately this one has been separated from all the remaining ones. Yeah. So this one will be splitted from all the remaining ones. Similar likewise for this one, likewise for this, likewise for this, likewise for this. So there is this one which will be splitted from n minus 1 other ones. So for each one we have n minus 1, n minus 1, n minus 1, and which in total is n times. And we are counting each pair twice. Like for this one, if we check, okay, for position 1, we are also counting for position 3. And when we go to position 3, we are also counting for position 1. So we have counted the pairs twice. So we just do upon 2 for the whole expression. So that would result into n into n minus 1 upon 2. So that is how this formula comes. Okay, so I guess this is easy to understand. Also, one more observation in this particular problem is like not an observation, but something which you can use in future problems. If change this expression, answer equal to recurrence. So instead of min, I change it to max. What would happen? Can you let me know in the chat? This is not the min cost right now. This is the max cost. Similar for here. What will happen when I change the recurrence relation from min to max? Can someone answer in the chat? I guess there are no responses. So you can take this as a homework as well. The answer won't change. This is a really important thing. The answer won't change. The minimum cost will of n will be equal to maximum cost of n. You can take this as a challenge yourself to prove why this works. Now I will move to the next problem. So third problem of the day, minimum bitwise OR from the grid. So you have been given a 2D integer array grid of size m cross n, and you must select exactly one integer from each row. Do you have any doubt in the second problem, Sushant? We need to prioritize the MSB. Yes, I will cover that in the third one. Yes. Okay, so we have been given a 2D integer array grid of size m cross n. You must select exactly one integer from each row of the grid and return an integer denoting the minimum possible bitwise OR of the selected integers from each row. Okay, so for this, I assume that you have sufficient knowledge of bit manipulation. Let's create our matrix, and for now, I will create a matrix 2, 3, 4, 4, 5, 6, 6, 7, 8. I will also write it into its binary form so it's easy for us to understand. So what is 2? 2 is 0, 1, 0, right? 3 is 0, 1, 1. 4 is, what is 4? 1, 0, 0. Sorry, I will just use this. So this would be our matrix in the binary form. So they have asked us from each row of the grid, we can select any one integer. So let's say I select any one integer at random. I will select it in the corresponding binary matrix, so it's easy to understand. And we have to return an integer denoting the minimum possible bitwise OR. For just now, let's see what bitwise OR means. So bitwise OR means if I take elements 0, 1, 1, 1, 0, 0, and 0, 0, 1. So the bitwise OR of this element should be 1, 1, 1. At any bit position, if at least there is one set bit, then we will set that particular bit in the answer as well. Here you can see there are two set bits, so we have set that bit in the answer. Here there is one, here there is one, so we have set the corresponding bits in the answer as well. For two numbers, let's say 1, 0, 1 and 1, 0, 0. The OR of these two numbers would be 1, 0, and 1. So I guess you know this much, that how to calculate the bitwise OR. So what they have asked us is you have to select any integer, like you can, it's at your own discretion which integer to select. But after selecting a single integer from each of those rows, the ultimate bitwise OR should be minimum. This is our problem. So in this types of problems, one thing to notice is if any row is all elements with set, but in that place, then we are forced to take one at that place. We need to prioritize the MSB bit as we move from MS LSB. That's one extra. I guess I will first complete my explanation. Then if you have any doubts, then you can paste it into the chat. So in this type of problems, what you have to focus upon is, let's say you have been said you have to maximize something or you have to minimize something using some bitwise operations such as AND or X. Like you have these type of operations and you have to either maximize or minimize something. So in this case, always go from MSB to LSB. This should be the first idea which should come to your mind. Why MSB to LSB? Let's see. Let's say we have a 5-bit number which is 1111. So the corresponding value in decimal of that bit would be 1, 2, 4, 8, and 16. Now let's do a prefix sum from reverse, and you can see the prefix sum would be something like this. 16 is 31. So one important thing to notice here is if you check the value at position, let's say 3, you can always see the sum of the bits behind 3 is always smaller. The sum is the sum from bit 1, bit 0 and bit 1 is 3, while the value of bit 2 is 4. So it's always greater. Similarly over here, if you, this is B4, B3, B2, B1 and B0. Okay. So the value at B4 would always be greater than summation of B0 to B3. Generalizing this, this is something as B0 to B and minus 1. This is always true. So the maximum contribution which comes to your number is from the highest bit. So that's why we always focus upon MSB, which is the most significant bit of our number. Because if you want to maximize our number, like if you want to maximize our final value, then it is mandatory that you should always try to include the MSB in your answer as possible. Because if you don't include your MSB, then you will never be able to get a better answer using the remaining bits. Okay. So if you skip MSB right now, then in future you won't get any better value. So it's better to select MSB and discard all other values than to not select MSB in search of a better value in future. So that is the main point. Always select MSB. It's okay if you have to discard the future elements, but always select MSB if you have to maximize, and always discard MSB if possible if you want to minimize, because that will have the maximum contribution to our answer. So that is the first thing. Next, so we have this one particular observation that we will start from the most significant bit and we will move on to the least significant bit. But how to select numbers based on that? So we know we have to select at least like one number from each row, right? So what we can do is, let's say I am on bit position 20. Why I'm taking 20? Because 2 to the power 20 is approximately equal to 2 into 10 to the power 6, which is well above our given input range, which is 2 into 10 to the power 5. If I'm no, it's just 1 if I. Okay. So this number is comfortably larger than our whole range. So we can start from this. So this is actually B19, which would be 2 to the power 20. So if we select one number from each row, let's first check for the MSB, that is bit at position 19. Position 19. Now I will go through the whole array, like whole grid. I will go through the whole grid. If there are n cross m elements in the grid, I will go through the whole n cross m elements of the grid. And for each row, I will try to find at least one element which at least one element which has B19 off. If here exists one element which has B19 off, in this row also there exists one element, in this row also there exists one element, in this row also there exists one element. So in total, in each row there exists one element where the bit at position 19 is off, then and only then the overall bitwise OR. Let's say we have values V1, the OR of this with V2, the OR of this with V3 till Vn. The bitwise OR will only result in like the 19th position would be off only if 19th position was off in all of the given values. For all the elements selected, the position 19 was off. Then only the final answer will also have the position 19 as off. So we will try to find at least one element in each row which will have position 19 as off. But then there comes a caveat. What is the caveat? Let's say in the past, we already selected some other element from the same row, and they might clash. So how to handle that? This is the best thing. Okay, for bit 19, you can say, oh, the bit 19, it's like I have found one element in each row which have their 19th bit off, and if I do a combined OR of all of them, then the resultant answer will also have bit 19 off. But we have only found this out for bit 19, right? What if all the elements had not only bit 19 but also bit 17 and bit 13 off as well? So and it wasn't the 111 first element, but it was some other element 222, and their bitwise OR had the like 1979 30 all off, and this only had the 19th bit off. So we had a better answer ready, but we didn't find it using this method. Like if you only check for one element, then we were unable to find it. So we will have to keep a track of the past operations which have we have done, or the past elements which we have selected, and at the same time look, okay, so when I go to next number, how can I find a improvement? I have to find a improvement. So the earlier bits which I selected, okay, I have recorded that 19th bit should be off. So in the new number also 19th bit should be off. If let's say I have found an answer, if 19th and 18th bit were off in the answer. So when I'm trying to look for a better answer, in that better answer as well, 19th and 18th bits should compulsory be off, and any other element which we are currently on. So we have to maintain this mask, which will say, okay, this mask would be of 20 digits, like 20 bits, because our number is like our number can be sufficiently recorded in 20 bits. So we'll keep a mask of 20 bits, and we will initialize this mask with all ones. That means, okay, initially this is our minimum value. Then I will check, can this bit be turned off in all the numbers? If yes, I will turn this off. Then I will go to the next number, and I will again try to see, okay, let's say I am on this particular index. Just give me, yeah. So initially I will have a long 19-bit number initialized with all ones. Let's say for now, let's keep it small for now. B0, B1, B2, B3, B4, 5, 7, and 8. Okay. So let's keep it this 9-bit number only for demo. So first I will go and see, okay, can I turn this bit 8 off using a single element from each of the row? If yes, then I will turn this bit off. Now when I go to B7, then again I will check for each row. Can I make not only B7 0, but also B8 should be 0? Is there such a number satisfying both of these conditions? If yes, then I will turn it off. But if no, then I will not turn it off. And let's say we didn't find any number, so we won't turn it off. Then let's say I go to B6, I don't find any number, I go to B5. Now for B5, I check, is there any element in each row satisfying the condition that B8 is off and B5 is also off? If yes, then I will turn B5 off. And let's say we found it, and we will proceed, like we then proceed to B4 and check, is there any element which has B8, B5, and B4, all of those as off? If yes, then I can turn it off. If no, then I will just continue. So in this fashion, if I continue, then it is always guaranteed that since I'm going from MSB to LSB, since I'm going from MSB to LSB, I will have forced the minimum outcome. I will have forced the minimum outcome, because we have already removed the most significant part. And after the most significant part, if there was a clash, then we have again went to the second most significant part, which was removable, and so on. So since we were removing the highest contribution at each step possible, the outcome would ultimately be the minimum possible. So that is how we have forced the minimum possible outcome. And we can see in the constraints that the product of n into m is 1if, and the number of bits upon which we are iterating is at max 20. Instead, you can denote this as log base 2 of n, and this was n, right? So ultimately, our solution would run in n log of n. So this is the approach for this particular problem. Now, if you don't have any issues with the logic, then we can move on to the code. So this was my code. Is it? So this is my function. I'm taking the grid. You can just regard this n and m. So initially, I have considered that my answer was a 20-bit number with all bits initialized with 1. As I said, my initial answer was this. This was my initial answer. All bits initialized with 1. Then I'm trying to turn off bit from the MSB to LSB. So I go from the most significant bit at position 19. I iterate till 0. Then I temporarily turn this bit off. I will turn off the bit at position 19. So I am actually using the XOR operation over here. Answer XOR 1LLI equal to 1LL left shift I. This is actually not recommended much because what XOR does is if this is my numbers X and Y 1011 1100. So the XOR table is like this 10100 is 0. So the actual XOR operation does if the both numbers are different, then it returns 1, and if both numbers are same, it returns 0. So in this particular use case, when I was on a current bit I, it was guaranteed to be 1. When I first come on a bit and check for that particular bit, then it was guaranteed to be 1. So when I turn it off, the operation would be 1 XOR 1 always. And that's why it goes to 0. So since I can guarantee that whenever I am coming on a number, the number was already 1. So that's why I can use this particular trick to turn off the bit. But usually you should not do this. You should use the AND operator to turn off the bit. What you can do is create a mask like this 1 1 1 1 1, and at the exact position where you want to turn off, you can place a 0, which is nothing but 1LL left shift I and inverse of that particular number. And if you perform a AND with this particular operator, like this particular number, then that bit would be turned off. So it's recommended to use this particular way rather than this one. But if you are fluent in bit operations, then I guess that's not an issue for you. So I'm turning the ith bit off temporarily, and I'm checking if there are some more numbers which satisfy this condition that the ith bit and the bit which we have turned off earlier are all off in the new number. So I'm iterating upon each row of the grid. For each row, I'm checking the XOR, I'm checking the bitwise OR of the value in the row with my current mask. Okay, so if X or temp is equals to temp, if X or temp, if X bitwise or temp. So let's say my temp was 11011011 and my X was, let me draw two test cases 011011, and in one case I have 001010, and in another test case I have 100000, and I'm currently on this position, the B2. This is B2, right? B2. So if I'm on B2 position and this is my X and this is my temp. So I can see, okay, X has this particular bit off and temp also has this particular bit off. And in the second case also, X and temp both have this particular bit off. So both are fine, right? At first glance, it looks okay, both are fine, but not. Because in temp, we had already turned off the most significant bit over here. And if I select this particular X, then this would turn on the most significant bit, which we don't want because the value from the most significant bit is the highest. So initially it was kept off. So in this approach also we will have to keep it off only. If it's possible, then well and good, we will go this way, but we will never do this. This is wrong. So how to check this condition? You can easily check this condition by bitwise OR of X and temp. should be equal to temp. If this condition satisfies, then that says, okay, the set bits in X is a subset of set bits in temp. That means there is no position in temp. There is no position in temp where temp is 0 and X is 1. So this is this condition. So we are checking for this particular condition over here. If bitwise OR of X or temp is equal to temp, then yes, we have found one element and we will break from that particular row. And then I'm checking, okay, is there a element in this row? If there is no element at all, if my flag 2 is false, that means I have found no element in this row. Then that means no, I cannot turn off this bit. And if I can turn off this bit, then I will like I have initially turned off that bit temporarily, but I will keep it as permanently off. But if I have not found, then I will not erase that bit. So that's how we are building our answer from the most significant bit to the least significant bit, and ultimately we would just return the answer. I guess this is clear to everyone. Okay, I can see some solutions in the chat from you guys. So I will, I assume that everything's clear. So let's move on to the last problem. So the today's last problem was also a bit on the easier side. It was a 6 pointer. The contest was overall easy, but uh, don't be disappointed if you haven't solved this particular problem. Like easier in terms of most of the contest, but still it needs some good observations and a really good trick from STL, which will help you. So the question is count subarrays with k distinct integers. In fact, you might have already heard this problem, right? Subarrays with k distinct integers. This is a fairly standard problem which many of us have solved using two pointers. Give me a +1 in the chat if you have solved this particular problem. Subarray with k distinct elements. Ignore this frequency condition, just the subarray with k distinct elements. I guess most of us have solved this particular problem using two pointers. So in this particular problem, there is one more condition. The distinct elements should be k. This is the first condition. Count should be strictly k. Strictly k. And the second condition is second condition, each element in that subarray has frequency greater than m. Frequency greater than m. So these are our two conditions. This most of us might have already solved from on LeetCode, but this is something new. So how can we approach this particular problem? So let's first take a subarray. We'll take this only 1, 2, 1, 2, 2. Let's take this subarray. Let's take this array, and where k is equals to 2 and m is equals to 2. So we know that this problem was solvable using two pointers. So maybe we can just extend that particular idea and try figuring out something. So let's start. We will initialize with L equals to 0, R equals to 0. So let's start. I start over here, then this is my L, then I can see the number of distinct counts in this range from position 1 to 1 is only 1. So I will increment. Now k is equals to 2 for this particular window, but frequency of each element is not sufficient. So again, I will go ahead. Now I can see that for 1 the frequency is sufficient, but for 2 it's not. So again I will go ahead. And in this case we have found okay, this satisfies our condition, so I would do a answer plus plus. But what to do now? Should I, like in normal two pointer setup, if we find one particular answer, then we either move left pointer, like we store the answer and then we increase the left pointer. But here you can see, instead of incrementing the left pointer, if I just increment the right pointer, then that would also be our valid answer. This whole range also satisfies the condition. So we have a dilemma. Should I increment the left pointer when I encounter a valid window, or should I increment a right pointer when I find a valid window? So how, like, what to do now? Should we increment left? Should we increment right? Or should we just discard this approach or go to another solution? So let's try to find some observations. So this is the first step. Let's try to find some observations. You can see for both of these conditions to satisfy, there is one invariant. What does an invariant mean? Invariant means things which never change throughout the problem. So invariant, which you can see, is both of these subarrays will have at exactly k distinct elements. Both of these subarray will have exactly k distinct elements. The size of these subarrays might be different. As you can see, this whole range contains two distinct elements. But inside this whole range, if I take some other ranges, like I take this one, or like I take the whole range, then the size are different. They both satisfy the conditions. So the invariant which does not change, it's exactly k distinct elements. The inner side might change, but the outer side is always same. So we can say this is like for a set we have superset. For a subarray we don't have a super subarray kind of thing. But this subarray second will always lie second subarray will always lie inside the first subarray. This is the first observation. So what new observations we can see? Okay, so another observation which we can see is if I start any particular L, okay, let's take a bigger test case where we can actually see this clearly. The previous one was 1 2 1 2 2, right? 1 2 1 2 2 1 2 1 2. So if this is our subarray, then if I am standing here at L equals to 0, then what is the minimum index to the right which satisfies the first and second both the conditions? So it would be over here, right? This index satisfies the conditions. Frequency of 1 is 2, frequency of 2 is 2, and the distinct count is also 2. And what is the furthest index to the right which satisfies this condition? It would be over here, right? Then if I'm standing on L, then the total number of subarrays which satisfies this condition would be all the subarrays starting from here and the end till here. So we have total number of ends is 1, 2, 3, 4, 5, and 6. We have total 6 subarrays possible if I start from position 0, right? Let's say if I added another integer 3 at the end. So I cannot take 3 in this uh, window which is starting from L equal to 0, because the number of distinct element would increase to 3. So I cannot take 3 into the same windows. So if I just remove 1 and I increment L pointer to here, L equals to 1 right now, then again the frequency of distinct element is 2, so still I cannot take this 3. But now as you can see, if this was my earlier R1 and if this was my earlier R2, now R1 will only move ahead and it will not move backwards, right? So here I can see the R1, the state of R1 has changed. Initially, R1 was sufficient to fulfill the second condition, but now R1 is not sufficient. What we need is we need one more occurrence of A. So I will erase R1 from here. I will move it forward until it satisfies the second condition as well, and it would be somewhere over here. And for R2 also, I will try to increment, but R2 we can see that we cannot increment further because it would increase the distinct count. So R2 would stay stationary in this case, but R1 will have increased. So you can see in this test case that R1 will only move towards right. And similar for R2, R2 will always move toward the right because you know the this R2 is the pretty standard one, right? The count of distinct elements which we have solved. So the R1 and R2 will both always move to the right, and L is also moving to the right. So whenever there are two variables and over the whole iteration, over the whole solution, if L travels a distance of n, R travels a distance of n, then it's linear in time complexity. Here we have just added one more pointer. So instead of 2 pointer, it's a 3 pointer now. But still the solution would be like 3 times n, which is O of n. So we have made our way to a like some part of the solution. Like instead of 2 pointers, if we keep 3 pointers, 3 pointers, the first pointer would be start of range. Pointer would be the start of range of the range. The second pointer, which is R1, it would be the minimum index R which satisfies the second condition. Minimum index which satisfies second condition. And the third pointer, which is R2, it would be the maximum index which satisfies first condition. First condition. And any subarray which ends between R1 and R2, it will satisfy both of these conditions because R1 is minimum index which satisfies and R2 is the maximum index which satisfies. Instead of first, I can write both over here. And here also I can write both. But actually we are just focusing on the, here we are focusing on the first, here we are focusing on the second part. But it actually satisfies both of these conditions because since second is a subset kind of thing of the first, so if second is satisfied, then first is also satisfied. And since R1 is the minimum, then anything which comes ahead of R1 and satisfies the first condition will also satisfy the second condition. So that's why R2 will also satisfy both the conditions. So actually, these are satisfying both the conditions, but the boundaries are defined like this. Minimum index which satisfies second condition and R2 is the maximum index which satisfies the first condition. It's clear to code it that way to get a better mental model. So that's what we will be doing in our code. So let's go through our code once. I have actually coded it in VS Code. For problems like this, when the solution like have lots of implementation, uh, you can just switch to your local ID because you need to debug the output sometimes, right? So this is my custom implementation of 2 pointers, which I have learned from somewhere. So let's go through this same implementation. Just what I will do is to stop more. Yeah. So yeah, my head one means the right pointer. Actually, let me just rename the variable names for so it's easy for you to understand. So actually, my head one is R2. My head two is R1, and my tail is my left pointer. So this way it's easier to understand for you. So this would be the exact same mental model which we have seen in this problem. We are iterating upon each L. For each L, we are trying to find the minimum R1 and the maximum R2. Then the subarray count would be all the possible ranges which end between R2 to R1, which would be nothing but R2 minus R2 minus R1 plus 1 would be the number of valid subarrays which contributes to the answer. So what I'm doing is I'm iterating upon the left pointer. So my left pointer starts from 0 and it goes on until the last of the array. So this is my start. So okay, if my left pointer starts from here, obviously I need to check for all the arrays starting at the left pointer, right? So it will go from position 0 to position n minus 1. So that is my left pointer. I'm iterating upon the left pointer. And inside, I'm first iterating my R2 pointer. R2 pointer means the maximum index which satisfies the first condition. What is the first condition? Number of distinct elements should be strictly equal to k. So this first condition R2 plus R1 is less than n. What does that mean? This simply means the next element exists. R2 plus R1 is less than n. That means R2 is less than equal to n minus 1. That next, the current R2 I am on, the next element should be inside the range. It should not be out of the bounds. This is the first condition. And the second condition is I have a map of integer comma integer which stores the frequency of each of those elements. So I'm checking if element is already present in the map, present, then distinct count won't increase. So I can take that element. Or else, if the element is not in the map, then I can only take the element if current distinct count is less than k. So these are the three conditions which we will be checking while incrementing the R2 pointer. It is R2 denotes the maximum subarray where there exists strictly k distinct elements. It does not focus on the frequency. It only focuses on the distinct frequencies, like how many distinct characters are present. So with this, we have found our R, R2 pointer. And for that, we have used a map of int comma int. In this solution, we have actually used two maps in a normal distinct number of distinct elements in a range. We use a single map. But since we have two distinct ranges which we have to maintain, we have this first range which starts from L and ends at R1, and we have a second range which starts from L and ends at R2. So we need to maintain the elements, maintain the frequencies or whatever stuff. We have to maintain it for two different ranges. So if we have to maintain something for two different ranges, we would obviously go with two different maps. You cannot store data or aggregates for two different ranges in a single map, right? So that's why I have used two different maps. I will also rename this for R2. I will use map2 uh, map for R2, and this is map for R1. So here also I am checking some conditions while incrementing the R1. The first would be obviously the next element should exist. The second condition would be the number of distinct elements is less than k. If the number of distinct element is less than k, then I will have to increase the range. Distinct count is less than k. Now there is one more variable which I have created, which is valid count. and that valid count will keep a track of number of elements with frequency greater than equal to m. So whenever I encounter a number whose frequency in the given range reaches m, then I will just increment the valid count by 1. Valid count is less than k. So if this condition satisfies, then I will increment the R1 pointer. Like both of these conditions needs to be satisfied, right? So if any of them is not true, then I will just increase. Like if size is less than k, then also I will increment. Or if valid count is less than k, then also I will have to increment. I cannot just check, okay, one satisfies, then I can continue. So that's why they are inside the OR operator. If any of them fails, then increment the right pointer. And we can only do that when the next element exists. So this is the condition for incrementing the R1 pointer. So when I'm incrementing the R1 pointer, I'm storing it in the map, I'm increasing the frequency. If the frequency is equals to m, you can also just change it to greater than equal to m. Oh no, actually you should just keep it m. Sorry. Uh, if it is m, it just has passed the m point in frequency and we can increment the valid count by 1. So we are maintaining the valid count while incrementing the R2 pointer. Now, if the R1 map size is equal to k and valid count is also equals to k. What does this mean? This was my R1 pointer, right? This over here. This was my R1 pointer. So if my map of R1 consists of exactly k distinct elements and each of the elements have frequency like greater than m. The count of such elements is also k. If both of these conditions satisfies, then I will add to the answer the ranges which ends at R1 and R2. All the ranges which ends in this particular setup, I will add them to the answer, which is nothing but R2 minus R1 plus 1. So I'm adding them to my answer. Then after my whole setup is done, after I have added them into the answer in this particular part of the code, I will move on to the next part, which would be incrementing my left pointer. So while incrementing my left pointer, I will have to take into account some things. First, I would have to remove from map of R1, I have to remove it from map of R2, and I will also have to handle the valid count by like decrement. If I have to decrement the valid count, I will also have to handle that. So first, I would remove that element from map of R2, and if the frequency of elements reaches 0, then I will also erase it from the map. And similarly, if R1 is greater than equal to left, then I will map of R2 np dot erase nums of left, and then again I will have to check it from map of R1 as well. But while checking for map of R1, I will have to check for the valid count as well. If valid count goes less than equal to m, like if frequency goes less than m, then I will have to decrement the valid count, because now the element will have frequency less than m, so I cannot count it inside the answer. So we will have to check for that specific condition as well while incrementing the left pointer. So I'm checking that condition over here. And in case if the value turns 0, then I will have to erase it from R1. So these are the two conditions which I need to take care of. Actually, three if we count map of R2 as well. So this was an implementation heavy problem where you have to take into account various edge cases and implement it carefully. And in the end, after checking for all the conditions, after handling all the data structures, both the maps and the valid count, I will just increment the left pointer plus plus. And this is just extra edge conditions. If in this case, conditions might not always get triggered. The condition is when my left pointer is ahead of right pointers, then that means I have encountered an empty subarray. So what I need to do is I just need to increment L by 1 and initialize R again to 1 behind of L. So you can actually see in my code, I have initialized R2 as -1, R1 as also -1 and left as 0. So what does that mean? That means if this was my array, then my L pointer actually starts from position 0, but my R1 and R2 starts from position -1. So this is just an implementation level detail, because sometimes what happens is when you are trying to count the number of subarrays, there might be subarrays which there might be zero subarray, there might be an empty subarray. There is no actual given subarray which satisfies this condition. So if you start with L equals to 0 and R equals to 0 as well, L equals to 0 and R equals to 0 as well, then if you do R minus L plus 1, it will give you 1. And if you add it to your answer, you might have added something extra which was not needed. So to handle that particular edge case when there exists no subarray, the answer is an empty subarray, I initialize the right pointers by -1 and left pointer with 0. And whenever if I haven't encountered an actual subarray, I just increment L by 1. In that case, my R1 and R2 would still be behind the L pointer. So I increment them to 1. I just set it back just 1 behind the left pointer. So this is the same condition. If R2 is behind left, I would just set R2 to 1 behind of left, and similar for R1. So these are the edge cases which you need to take care of. So ultimately you can see it was the logic itself wasn't that difficult to figure out, but the implementation is like surely a bit on the difficult side. You need to have strong implementation skills to handle this kind of problems. If you miss any of those conditions, like there are various conditions which you need to check for, and if you miss any of those, you are off by 1. Instead of greater than equal to, you place just greater than, or you don't handle these edge cases properly, then you will get a wrong answer. So be very careful. In fact, if you are not really good in implementation, then one advice which I can give is first write comments in your problem. Like first figure out what you want to actually do, what you want your code to do. First write it in plain English, and then you can proceed like this. In fact, that is how I started. I first used to write what I wanted to do. Then I would just implement those conditions. As you can see, I know that I need to maintain these three conditions. And if I have written them out clearly, then I can just implement it one by one. So you can also proceed the same way, and then there will be a very low chance of you encountering a bug. So that's it for the post contest discussion of today. I hope you all understood the problems. If you have any doubts, please let me know in the comments and I'll be sure to respond. Thanks for joining everyone. Will be it from my side.